Turntables. We'll spin you right round, baby, right round. Steam engines. It might sound complicated, but actually, it's just a lot of hot air. Playground equipment. When it comes to it, it's all swings and roundabouts. And non-stick cookware. Except when I'm cooking, that is. But first. As the music industry went digital, the turntable seemed destined for the scrap heap. But this analog technology defied predictions and survived. With a sound that's arguably fuller and more natural than compressed digital formats, this retro technology is attracting new fans. In an age when media players are digitized and pocket-sized, the turntable plays on. The use of high-tech composites like carbon fiber puts a modern spin on this technology, bringing the record player into the 21st century. Production starts with a thick square of cast acrylic. The technician drills a hole in the center. It will be a reference point as he transforms this square into the turntable platter. A computerized tool cuts a circle shape out of the square. The disc then spins, while another computer-guided tool enlarges the center hole to size it for the platter's main bearing. The next tool precisely cuts the surface of the disc to give it the correct angle. Computerized tools transform this small aluminium disc into the counterweight's main component. The counterweight balances the tone arm to keep the stylus in the groove of an LP. They slope the surface and cut holes for attachments and for installing the part. Finally, they cut a triangle out of the circle. This takes the part to its final shape and weight. From a flat disc to a precisely crafted counterweight. Next, the platform for the tone arm takes shape. It's designed to cradle all the parts at the end of the tone arm, including a cylindrical housing for a spring mechanism and an egg-shaped housing containing a bearing. A technician now assembles the tone arm, beginning with a tapered tube made of carbon fiber. It's a high-tech composite that's extremely stiff, so there should be no structural weakness in this crucial part. The technician threads a pre-assembled wiring loom through the arm tube. It's special wire for high-frequency transfer. These wires have been encased in copper to keep out ambient radiation that would interfere with the tone arm's operation. The carbon fiber tube also insulates against interference. He mixes epoxy resin that he then dabs around the inner rim of the bearing housing, which has now been equipped with the bearing. He inserts the tone arm tube into the housing. The tube adheres to the glue-coated rim. But before it totally bonds, the technician scrutinizes the alignment. He makes adjustments if needed, and then he'll clamp the assembly to allow the glue to cure. With the turntable tone arm now upright, he solders the wires that are protruding from the joint to external wiring for the amplifier. And once all the connections have been made, he inserts the wires into the metal joint. Ensconced in this joint, the connections are well protected and can't be pulled apart. He equips the main counterweight component with two thick steel beams for balance. He slides the counterweight onto a third beam, which has been installed in the egg-shaped housing. This completes the turntable tone arm. Next, they encase the electric motor in its metal housing. And they build the record deck. They mount the motor to the two-tiered deck, designed to absorb any vibration. The aluminium subchassis is next. They link it to the motor with a drive belt. Then they give the belt drive system a test spin to confirm that it runs smoothly. Now they install the acrylic platter, felt mat and tone arm. With this turntable now fully assembled, it's time for the vinyl test. The record spins and the stylus traces the groove. The analog sound fills the room, proving that this technology stands the test of time, which is music to my ears, and yours, I hope. The first modern steam engine was invented in England in the early 1700s, helping launch the Industrial Revolution. Today there's a return to steam power. Due to its different configuration and combustion process, a steam engine produces less pollution than a regular internal combustion engine. The steam engine burns fuel in an external combustion chamber. The resulting heat turns water into pressurized steam that enters the cylinders, pushing pistons, turning a crankshaft that powers the drivetrain. Because this engine doesn't burn fuel inside the cylinders like a traditional car engine, it can run on any type or mixture of fuels with fewer emissions. The circular engine block is made of aluminium. Technicians install studs to hold 6 stainless steel cylinders. Due to the constant exposure to steam, all engine parts are made of rust-proof materials. The technicians insert a piston into each cylinder. The piston is aluminium, with a heat-resistant carbon cap and a glider to isolate it from the cylinder wall. They connect the piston rods to the crankshaft in the centre with a specially designed component called a spider bearing. This bearing is designed to modify the piston stroke, producing a smoother rotation of the crankshaft and more power to the engine. Unlike a traditional car engine, with cylinders arranged in line, these cylinders are in a radial configuration and therefore equidistant from the centre. This prevents the engine from warping under high temperatures. They place a counterbalance over the spider bearing to further smooth the motion of the crankshaft. Now they install a push rod over each cylinder. It operates a valve which lets steam enter the cylinder and move the piston. They insert the base of each push rod into a guide ring. Then attach the cylinder heads, each of which houses a steam entry valve. They insert the push rod into the valve. Then, to complete the assembly, they install the cam, which pushes the rods as the shaft spins. The factory hooks up every completed engine for a couple of rounds of performance testing. First, a trial run using air pressure to check for leaks and to verify that all the components operate correctly. If everything's fine, then they repeat the process with steam pressure. This type of steam engine can power many types of machines, from cars, trucks and boats to electric generators, as we see here. In a vehicle, it doesn't require a transmission because it produces so much rotational power. Now for the heat exchanger, the component which turns water into engine powering steam. Technicians use a motorized wheel to wind 6 meters of stainless steel tubing into a coil. They bind the coil with steel thread, putting a stitch in between each tube to create a minute gap. That way, when fuel burns in the combustion chamber, the heat can travel over and in between the tubes, heating the water inside faster and more efficiently than if the heat would contact only the coil's top and bottom surfaces. The result? Superheated steam in just 5 seconds. They stack 6 of these coils, one to feed steam to each cylinder. This nest of tubes forms the engine's primary heat exchanger. They test it using any number of fuels, even waste fuels, such as used motor oil and used vegetable oil from restaurant fryers. Virtually anything that burns will do. The fuel combusts at low pressure, not at high pressure, as in a petrol or diesel engine. That means burning fossil fuels to make steam produces far fewer greenhouse gases, and most hydrocarbons burn off completely within the sealed combustion chamber. You never have to refill or top up the water because a condenser cools the steam back into water, which then recirculates. Water also acts as the engine lubricant, so the steam engine doesn't require motor oil. Besides fuel combustion, this modern steam engine can run on other heat sources, such as solar heat and exhaust heat from furnaces or engines, which is cool. Or not, as the case may be. Coming up after the break, we'll be getting unstuck with non-stick cookware. And playgrounds, but not as you know them. Or not as I remember them anyway. See you after the break. There was a time when the playground equipment in the local park or schoolyard was pretty basic stuff. A set of swings, a slide, maybe a seesaw or two. Today's playground equipment is far more varied, imaginative and colourful, designed to stimulate children's minds as well as exercise their bodies. Slide down, climb on, wriggle through. There's no end of adventure for kids on modular play structures. Or on this bubble-bellied dinosaur. To make the dinosaur's neck and legs, an automated bandsaw cuts long steel tubes to specific lengths. The tube for the neck is 1.7 meters long. Workers curve it in a bending press. A level helps them get it just right. Next, they weld on two steel plates. These will support plastic seats on which children can sit. Workers also weld on bars for attaching the neck to the body. They weld anchoring tabs and support bars to the 4 steel tube legs. Workers sandblast the legs and neck with stainless steel grit. The sandblasting gun shoots the grit at a speed of 700 kilometers an hour. This roughens the surface to help the paint adhere. After applying an undercoat of grey primer, workers spray on a coat of plastic-based paint. The paint is then baked on, which maximizes its durability. Meanwhile, a computer-guided engraving machine carves an educational design into a panel made of triple-layered polyethylene plastic. Panels like this block the open sides of the playground equipment, preventing children from falling through. To construct the dinosaur's bubble-shaped body, workers bolt together 2 half spheres made of molded polyethylene plastic. They position the bubble body on the legs. Then bolt them from the inside. They bolt the neck to the body. The neck has since been fitted out with plastic seats and the dinosaur's plastic head. They finish off the dinosaur with a metal label bearing product information. This factory produces several components for its modular play structures, such as a climbing net made of galvanized steel cable. The hard cable is padded in polyurethane. Workers use hydraulic scissors to cut the required lengths of cable. Then a cable stripper to slice off about 3 centimeters of polyurethane from the ends of certain cables. Workers then cap each exposed end with a sleeved aluminium ring. They crimp the sleeve with a 40-ton press. The rings will be bolted to the play structure's frame and anchoring system. Finally, workers assemble the cables into a grid, locking each intersection with a plastic connector. To ensure they won't rust from exposure to the elements, the connector's central screw and corner rivets are made of stainless steel. On the modular play structure, the children walk on a platform. It's constructed from thick steel sheets, perforated by a robotic laser cutter. After bending the sheet in a press to the required shape, this is the corner section of the platform, workers heat it in an oven, then submerge it in a vat of polyvinyl, which instantly adheres to the hot metal. They build up a good coat, about 3 millimeters thick. Then let the excess drip off. They blast the entire piece with an air gun. This clears the holes and produces a textured anti-slip surface. Since playground equipment remains outdoors, all the paints and plastics are UV treated to resist fading. Besides being durable, the equipment is designed to meet all required safety standards, so that parents can have peace of mind while their children have a piece of the action. Go on, girl. Food just slides off non-stick cookware's remarkably slippery surface. In 1938, an American chemist was experimenting with refrigeration gases, and a waxy substance was formed. Years later, when bonded to cookware, it gained a non-stick reputation. When it's time to fry, using a non-stick pan averts a messy situation. The non-stick coating is one of the slipperiest solid materials on Earth. Called polytetrafluoroethylene, the name is a bit of a mouthful, but the appeal is simple. Food won't get stuck on this non-stick surface. To make the aluminium pan, they use 70% raw material and 30% leftovers from prior production of pots and pans. They fire it to a molten state and filter it to remove contaminants. The liquid aluminium flows into large vertical rectangular molds. A jacket of water around the molds cools the aluminium to take it from a liquid to a solid. A crane extracts the cast slabs. They're heading to a heating chamber to soften them. This will allow the metal to be shaped and formed. A saw slices the slabs in two and trims the ends. More blades scrape the top and bottom to remove impurities. A conveyor repeatedly feeds the shorter slabs to heated rollers. Guides at the side maintain the width, while the rollers compress the aluminium, taking the thickness down to about ½ centimetre. The rolling also elongates the slab. It starts out 2 meters long, and after a few minutes of rolling, it's been stretched to well over 100 meters. Pizza cutter style blades trim the edges of the aluminium sheet. Another roller winds the aluminium into a big coil. Then they unwind it and squeeze the aluminium to flatten it. Machinery now pulls the long aluminium sheet forward to a 120-ton punch press. This powerful press forces the metal around a frying pan-shaped die and then punches out the shape. The freshly formed aluminium frying pan falls onto a conveyor below. The leftover aluminium will be used to make new frying pans. The pans now travel on a conveyor through a washing station where they're cleaned and then treated with sodium hydroxide. This opens the pores of the metal to allow an enamel coating to stick to the outside and the non-stick finish to adhere to the inside. A worker inspects the pans and places them upside down on spray fixtures. It's a tight fit to shield the inside from the enamel spray that comes next. The pans spin on the fixtures and pass by the spray nozzles for an even application of enamel to the exterior of the pans. A glossy clear coat follows. The frying pans transfer to a dryer conveyor. The hot air extracts water from the enamel coating, and the colour goes from grey to chalky white. An automated squeegee silk screens the company name and other information onto the pan bottoms. They now enter a long curing oven, heated to 560 degrees Celsius. The cure toughens the enamel and deepens the colour so it turns grey and glossy. A suctioning device picks up the pan and turns it around for the inside coatings. A sprayer applies a special primer that will make the non-stick coating adhere to the pan. It then applies the non-stick coating. The pan receives 2 layers of this synthetic substance. The suctioning device releases the pan and it lands upside down. Then the pans journey through the oven again, to cure the non-stick finish at around 425 degrees Celsius. On exit, water rains down to cool the pans and rinse off any contaminants. Then they go through an infrared light chamber to dry off. From a plain shell to a pan with an enamel finish on the outside and a non-stick coating on the inside, the transformation has taken just 1 hour. A worker now aims a laser and aligns it with lettering on the bottom, allowing him to punch holes in a precise location on the side of the pan. He slides pins into the holes and slots them through holes in the handle fitting. Using a ram, he flattens the pins to rivet the handle to the pan. Now, no matter what's cooking, washing up should never be the chore it once was. So even I might have a go. Then again, maybe not. So, if you're all in a spin about turntables, which is sound, and you feel the need for speed and want to let off some steam, then perhaps what you really need is a trip to the playground, because now you know how it's made.